Let's take a few minutes and tell the story of this particle based on its graph, on the graph of its velocity. So we know that the particle is moving along the x-axis, starting at the origin when t equals 0. The velocity of the particle is given in the graph or in the table. No, this is the velocity of the particle. Displacement would be something measured in centimeters. That's a distance rather than centimeters per second. This is how fast the particle is moving at any given time. So the particle is moving along the x-axis starting off at x equals 0 when t is equal to 0 seconds. The velocity of the particle is given by this function, v of t, in centimeters per second. A positive velocity indicates particle moving to the right. So negative velocity indicates that the particle is moving to the left. So our starting position is at x equals 0. Which direction is the particle moving? It starts off moving to the right. Tell me about the speed of the particle. What's happening to the velocity of the particle as it begins moving to the right? What's happening? The velocity is increasing because we can see the velocity starts off at 0, then it starts increasing, and for the first second, it increases. What kind of increase are we seeing? How would we describe that acceleration, the change in its velocity? So notice that the velocity is just a line with a slope of how much? 4. The slope of the line will be the rate of change of the velocity. And what do we call that? Acceleration. So already we have some information about the acceleration. We can see that the particle is moving to the right, it's speeding up, and we have more detail about how it's speeding up. The velocity is increasing with constant acceleration because we're looking at a line. The velocity is creating a line. That means we're moving with constant acceleration. Great. So for the first second, the particle's velocity increases from 0 centimeters per second to 4 centimeters per second under constant acceleration. In that first second, we've got questions about the velocity. We see the velocity increases. We can describe how that velocity is increasing. It's increasing under constant acceleration. Is there a position question here? How far did it go? And how do we know? How far did the particle go? That would be a question about position. Where did it end up? After 1 second, it's moving to the right. After 1 second, how far was it from what starting position? 2 centimeters. Where'd you get 2 centimeters from? Area under the curve. Awesome. Derivative is slope of the tangent line. Integral is area under the curve. All that stuff means something. We've got rates of change. So we have a lot of information about that first second. The particle began at 0, increased, moved to the right under constant acceleration. The acceleration would be 4 centimeters per second, otherwise known as 4 centimeters per second squared. And the distance traveled is 2 centimeters to the right. So after 1 second, the particle is 2 centimeters right. So at +2. Between 1 and 2, what's happened? What is the velocity telling us now? The velocity is decreasing. Which direction is the particle going?
It's still going to the right.
Still to the right. Just because the velocity changed direction, that doesn't mean that the particle changed direction. The particle is still moving to the right because the velocity is still positive. How far does that particle go between second 1 and second 2? Also 2 because of the area. But tell me about the acceleration of the particle. The acceleration is not decreasing. The velocity is decreasing. What kind of acceleration are we seeing?
Negative.
The acceleration has switched signs. So the acceleration is negative. The velocity is still positive. So the particle is slowing down. from its maximum velocity of 4 centimeters per second back down to 0 centimeters per second. How far from it, the origin, is the particle now? 4 centimeters to the right, so at +4. What's that? Yeah, it's a little bit jarring because it's accelerating, and then there's a little bit jarring when it switches, because now it starts decelerating. We notice that our velocity is not differentiable at 1. So if I wanted to ask a cheap question, I could say, what's the acceleration at t equals 1? But because there's a sharp corner there, our function is not differentiable at 1. So I can't tell you how the velocity is changing at 1. It instantly, our acceleration instantly goes from +4 centimeters per second to -4 centimeters per second. So our derivative is discontinuous. So our function is not differentiable. All right. And then at 2 seconds, what happens? So at 2 seconds, let's see, we were 4 centimeters to the right. So we're standing here at +4 with our particle. What's the particle doing now after 2 seconds? Now we're moving back to the left, and that's the direction it's going to keep going for the next, as far as we can tell, for the next 3 seconds. So between 2 seconds and 3 seconds, what's going on? We know it's moving to the left because the velocity is negative. Describe the acceleration of the particle. No, the acceleration is not increasing. It's negative. The acceleration is negative. What's the slope of the line we see between 2 and 3? -2. So we could say that the acceleration is -2 centimeters per second per second. But the acceleration is constant because our velocity is a line. The acceleration is the slope of the tangent line, and since we have a linear function for the velocity, our slope is constant. So once again, at 2 seconds, we have our velocity is not differentiable because our velocity went instantly from -4 centimeters per second squared to -2 centimeters per second squared. All right, then at 3, 4, and 5 seconds, which direction is the particle moving? To the left? How fast is it going? -2 centimeters per second. So its velocity is -2 centimeters per second. The speedometer on the particle is just reading 2 because it's a speedometer, not a velocityometer. And we can see from between 3 and 5 seconds, we would say that the particle is moving with constant velocity. So what's the acceleration? 0. Except the velocity is not changing, so the acceleration is 0. At 2 seconds, we were at +4. From 2 to 3, how much did our position change? -1. So our position is 1 unit to the left. So we went from 4 down to 3. And then from 3 to 4, how much does our position change? Not by 1, 2. So the area between 3 and 4 is going to be 2. So it's going to be 2 more units. Now we're at 1. And then from 4 to 5, another -2 to another -2 or 2 to the left. So now at 5 seconds will be 1 unit to the right. Where did we cross the x equals 0 again? In between 4 and 5. Where in between 4 and 5? Can we even tell? Can we tell? In this case, we can't. How can we tell? How do we know that it's going to be 4.5 seconds that we cross the x-axis. That's where we cross, not the x-axis, excuse me, cross the origin again. How do we know that the area is going to balance out that way? Oh, that's a good observation. We got this triangle here, and then we got a triangle. And so the triangle has an area of 4. We just have to build out 4. So that happens at 4.5. But how can we get so reliable that 4.5? What's another way we could think of that 4.5? That's good. Observing with the area, that's the distance traveled. We back at 0 when we've gone 4 units to the right, and then 4 back to the left. So we know that that happens at 4.5. Notice that between 4 and 4.5, we got this -1. And then from 4.5 to 5, we got another -1. One of the reasons that this is going to split the difference is that if we have the derivative is constant, that means our function is linear. And so we're just going to be drawing a line from a position at +1 to a position at -1. So we're just going to connect that with a line. It'll cross at 4.5. So there's a couple of ways that we can get it at 4.5. I like the area one that uses more calculus, even better. Any questions? So there was a lot going on with the story of this particle. We talked about the direction that the particle was going based on the sign of its velocity and whether its position was increasing or decreasing. We talked about the acceleration of the particle by looking at the slope of the velocity graph or the rate of change of the velocity. We were very careful with how we phrase things. We talked about the velocity increasing with constant acceleration. The acceleration was never more than just constant acceleration. We never had like linear acceleration. It was just +4, then immediately -4, then -2, then 0. So our acceleration graph is just a bunch of horizontal line segments because our velocity graph is just a bunch of line segments. Acceleration is the rate of change of velocity. So that's the tangent, the slope of the tangent line. And the area tells us changes in position. Look how much calculus we threw at this, just telling the story, reading the velocity graph. This is why we spent all that time with sign, direction, concavity. Now, the other thing that we should include is what does the graph of the position look like? And I have that here where we describe the concavity. So there's our area being the amount of change. Here we have concavity, concave up when the velocity is increasing, concave down when the velocity is decreasing, concave down because it was still decreasing. And then we have linear, that is no concavity from 3 to 5. Any questions? Replay that story as you look at this velocity graph and think about some questions that you could pull out. What kind of questions does that story lead to? Just like when you were doing reading comprehension. You had to read a story and then answer some questions about the story. That's all we're doing here. We just had to translate the story because the story was presented with a graph. There's also not a lot of character motivation here in the story. It's just a particle going. So maybe if you're more creative, you can come up with an entire story for the particle's motivations and feelings about things. Like it started off and it was really excited, so it's accelerating, but after 1 second, it's like, oh man, should I really be doing this? And that's why it starts to slow down. I don't know. And then at 2 seconds, it turns around. It's like, oh no, I need to go back. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.